All right. So we finished right there last time. We keep wrapping this up. Now, the difference between the first half of the section and the last half. On these problems, it says find. Anywhere you see the word find, you must start from scratch. You must really make up the whole series. The remaining part of the section says use power series, like this problem. Use power series. Integrate by using power series. If the problem does not say find a power series, you could use this table that I will provide on your test. Actually, it's already on the formula sheet. It's on page 808. And it has formulas for each of those. 1 over 1 minus x, e to the x, sine of x, cosine of x, inverse tangent. So those are going to come up in the next sections. We didn't touch on all of those. We really did this, and inverse tangent in this section because a derivative of that looks like 1 over 1 minus x or some kind of that form. The remainings are coming up. E to the x, sine of x goes actually for anything else. So, if I look at the next problem, number 29, direction states, use power series to approximate the definite integral to 6 decimal places. Well, the deal is, if I look at this right here, that's what I copied right here. Notice you have both the expanded form and the series. So, I know what the tangent inverse of x is. In this case, all what I have to do is modify it to match what is the inverse tangent of x over 2. That's going to be the integral from 0 to 1/2 of the series n equals 0 to infinity, negative 1 to the n, 2n plus 1. Nothing changes except instead of x, you're going to replace it by x over 2. And if I work this out, I know this is the integral from 0 to 1/2. This is the series n equals 0 to infinity, negative 1 to the n, times, and if I clean this up, that's going to be 1 over 2 to the 2n plus 1 times 2n plus 1, x to the 2n plus 1 dx. The only variable here is x. Everything else is considered to be a constant or treated like a constant. So, if I am to go ahead and integrate, I would figure out that this is actually the series n equals 0 to infinity, negative 1 to the n over 2 to the 2n plus 1 times 2n plus 1. Those are constants. Times x, I'm going to add 1 to the power. That will be 2n plus 2. Divide by that. Right? And if I really clean this up, I'm looking at the series n equals 0 to infinity, negative 1 to the n. Meaning, if I factor, actually, you know what? This is fine. No need to clean it up. As is. That's fine. So, this is the answer. That's what the integral equals. Now, there is a catch. When can you integrate? There's something about you can only do that if f is absolutely convergent. We don't worry about that in this class. So, if I really evaluate this integral from 0 to 1/2, this is what this will equal. 0 to infinity, negative 1 to the n over 2 to the 2n plus 1 times 2n plus 1 times 2n plus 2. Now, substituting the 1/2 in, that will get me an extra 1 over 2 to the 2n plus 2. So altogether, if you really think about it, this is actually the series n equals 0 to infinity of negative 1 to the n divided by 2. When I multiply those, I add the powers. That's going to be 4n plus, let me check really quick, 4n plus 3, 2n plus 1, I was going to really factor a 2 out of that, but then I don't want to confuse you more. So what is that? If I like n equals 0, that's 1 over 2 cubed times 1 times 2 minus n equal 1, I'm sorry, 7, 3, and 2 times 1, that's 4, plus 1 over 2, if I let n equal 2, that is 11, and that is 4, 5, and that is a 6, 1 over, and 2, that's add a 4 every time, that's 15, and that is 19. 1, 3, 5, 7, 9, 1 more, and 1 more. So my guess, this is where we're going to stop, probably here, I'm not sure, but let's see how that works. If I take 1 divided by parentheses 2 raised to the 15 times 7 times 8 equals, so I'm getting 1, 2, 3, 4, 5, 6, but that's a 5. When you subtract a 5, that's going to affect. So my guess, the next term, if I go back and if I throw in there a 19 and make that a 9 and make that a 10. Now I'll notice that, you know what, 1, 2, 3, 4, 5, 6, this is safe. So since that's a 5, when I subtract, it's going to affect. So pretty much put those in a calculator, and that would be the sum accurate to 6 decimal places. That's in absolute value the maximum error in this approximation. Alright? 26 is next. It says evaluate the indefinite integral as a power series. What is the radius of convergence? Well, I'm looking at 1 over 1 plus t cubed. I know that is the series n equals 0 to infinity of negative t cubed to the n. Automatically, negative t cubed should be less than 1, which indicates that t should be less than 1. That's my radius of convergence done. So this is the series n equals 0 to infinity, negative 1 to the n, t to the 3n. Now, if I multiply by t, I'll get this to be the series n equals 0 to infinity, negative 1 to the n, t to the 3n plus 1. So all of that work to get this integral n equals 0 to infinity, negative 1 to the n, times t to the 3n plus 1 dt. And what that would equal, sc plus the series n equals 0 to infinity, negative 1 to the n is a constant, add 1 to the power, divide by that. And there it is. If the problem says, if it doesn't say find a power series, you could use the table, you could use whatever you want. But if it says find a power series, you must start from scratch. The last problem, if I take this function f of x, and on the exam I'm going to say show that the function is a solution, I'm going to add by using power series. So you must use the actual series. You can't divert from that. This is a cosine, by the way. You can't say this is the cosine. Take two derivatives on a cosine plus the cosine and get a 0. So you're going to write f equaling. And if you look at that, you'll notice when you let n equals 0, you're going to get a 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. So the point is you need this because you need two derivatives. When you take the first derivative, do you notice that you lose a term? So we're not trying to simplify it. We're just trying to see, do we lose terms or not? So do you notice we lost a term? And when I take another derivative, do you see that in this case I don't lose a term? That's a must. You must be able to tell whether you lost a term or not. Oh, lovely. So, when I come in and I want to apply this, I'm going to take, this is F, it's right there. So this is, which color should I use? Okay, this is right there. But now I need two derivatives. If I take the first derivative of F, that's the series n equal 1. Where did I get the 1 from? Look on the right and you'll figure that out. I'm going to bring the power down, subtract 1 from the power. And when I take a second derivative, notice I'm going to leave it at 1 because I didn't lose a term right there. But I am going to bring the power down, subtract 1 from the power. Now, I want to take this if I factor a 2 out of the top, minus plus this, the original. Now there's only one way I could show that this series equals 0. That is to combine them and so show that the coefficient equals 0. To show this, if x equals 0, it's useless. So I need to combine those somehow. Well, there's a couple of problems. One, you start, the main is for those to match, they don't match. So I'm gonna shift this one up by 1. This will go up, this will go up, this will go up, this will go up, and this will go down to match. That's my first order of business. I want actually the x's to match really. I want this right here to match with this right here. I said it backwards. I don't care much about that, the indexes. So, if I shift this one up, replace n by n plus 1, that will be an n, so that's 2n. Shift this up by 1. If I throw an n plus 1 in there, that will be 2 into n plus 1 minus 1. That is 2n plus 1 plus 2 minus 1 is 1. 2 into n plus 1, negative 1 n plus 1 over 2 into n plus 1 factorial plus the series n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. I want that to equal 0. The good news, they both start at the same now, and they both have x to the 2n. I could get x to the 2n out. I could get the series n equals 0 to infinity. I could factor a negative 1 to the n out of both of those. I'll have a negative 1 out of the first times 2n plus 1 times 2n plus 1, oops, times 2 into n plus 1. Over. This is 2n plus 2 factorial. So I could say that is 2n plus 2 times 2n plus 1 times 2n factorial plus, out of this, I'll only have 1 over 2n factorial, x to the 2n equal to 0. So my goal is to show that this equal to 0. And if I look at that, I notice this cancel with this. And I'll say that's the series n equals 0 to infinity, negative 1 to the n, negative 2 into n plus 1 over, if I factor a 2 out of those, now this cancel with that. I'm looking at the series n equals 0 to infinity and negative 1 to the n. And can't I cancel those two? Isn't that negative 1 over 2n factorial plus 1 over 2n factorial? Guess what that is? And that would be a 0, so the whole sum equal is 0, and there's the whole.